13.3 on the back, we have a combination circuit. So we're going to practice an old school combination circuit using good old-fashioned physics reasoning to figure out what's going on here. So read the problem. It says, given the ammeter in figure P34 reads 1.0 amps, and that the EMF is the ideal DC source is indicated by the voltmeter. That's what we want to find. So I'm going to take a look here. I'm going to go, well, okay, so first thing I note is coming this way is 1 amp of current. That's what the thing says. Now, how do I know it's going this way? Well, first of all, see this positive into the battery. Positive in the battery, the current comes out of there, it goes this way, and then it splits. Some goes this way, some goes this way. And that current flows through here and has to go this way through the ammeter. So I'm confident, because no other batteries involved, the only way the current could have possibly be going is that way. Okay, so in agreement. So one thing this does tell me is right off the bat, it tells me that my potential difference or my voltage drop from here, this position here, to this position here, we know for parallel circuits it has to be the same, because an electron reaching this point right here must lose just as much energy whether it goes this way or that way. It has to lose the same amount of energy. So since it has to lose the same amount of energy, we know the voltage across here would be V equals 1 times 12. So therefore the voltage or the potential difference would be 12 volts. That said, we also know it has to lose 12 volts if it goes this way around the circuit, right? And so I can go V equals IR. And I can go 12. I know 12 has to be dropped across there is equal to I times 6. And so I get that the current this way, let me use a different color, yellow. I've got nice yellow current. Well, maybe I don't have yellow. There's yellow. All right, let's see if I can get it on here. So yellow, I got a current of 2 amps right there. Now if I have 1 amp going that north route, 1 amp going this way, 1 amp, and 2 amps going the other way, well, how much has to be going through this resistor right here? The current just can't disappear. So the amount flowing through here, if I've got 1 amp going through the top and 2 amps going through the bottom, there must be 3 amps going through that one resistor right there. And if that's the case, then I also know, by the way, on the backside, the same thing must be happening. There must be 3 amps coming out the backside. Now, remind myself right now that there has to be the same current coming out of and going into the battery for an ideal battery or basically any kind of battery. And so therefore 3 amps coming out this way, 3 amps going in is comforting, because otherwise I'd have a problem in the universe. Remember, they can only push the guy in front of them, so if 3 amps are coming out of the battery, 3 amps have to be going into the battery. It's pretty much a golden rule. Now that I've kind of laid out what the battery's doing, I reread the instruction. It says, what is the voltage across the battery? Essentially, what is this voltmeter right here reading? And so I'm going to go ahead and go, well, the voltmeter here is reading the amount an electron coming out, and again, electron would come out of this side of the battery, but a positive flow charge would come in this way around, would lose just as much voltage as if it went all the way through this big old mess. Now, if it did, it would lose how much going through here? Well, 3 amps are going through here at 4 ohms, so if you use a quick V equals IR, you get 4 times 3, which is 12 volts. So I get 12 volts going through there. On the back side, I have same sort of thing, V equals IR. I've got I've got a 3 amps, and I've got a resistance of 2. So therefore, my voltage is going to be 6. So if I lose 12 going through the first part, 12 whether I go this way or this way through the second part, and 6 go to the last part, my voltage I lose, every electron's got to lose 12 through that first one, 12 through the combination circuit, through the parallel system, and they have to lose another 6 going through the back side, so they're going to lose a total of 30 volts going through this system. And that's the correct answer, because that is also what they have to lose if they go this way through the system, and therefore the voltmeter would read 30 volts. All right, so that's how to do problem number 2. Let's start problem number 3. So here's problem number 3. Problem number 3 is a more standard form of this sort of equation for a combination circuit. Note the following, that an electron that can go this way or this way, and again, our electrons are really coming out of that side of the battery, but we're talking about positive flow. So positive flow charge can either go through this way or this way, so these two have to be in parallel. So I find the resistance total of this first arrangement is going to be 1 over RT equals 1 over 3 plus 1 over 6. I get 1 over RT equals, assuming I can do a fraction, I get 1/2, so RT must in fact equal 2 ohms. Since everything that goes through these two has to go through this one, those are in series. We know resistance in series adds, that's 2 plus 4, so I get 6 ohms of resistance is the total resistance of the system. Now, since the battery is 6 volts, I can quickly go voltage total equals current total times resistance total. I get 6 equals I total 6, and I forget that total current is equal to 1 amp. And so I've got 1 amp coming out of the battery and 1 amp coming into the battery. That also, by the way, means that I have 1 amp up here going through that battery, right, that light right there, and I've already got 1 answer done, right? What about these two? Well, if 1 amp is going through this one, then my voltage up there is going to be V equals IR, or V equals 1 times 4. So every single particle of charge that goes through this thing is going to lose 4 volts just getting through that one resistor, which means that they only can lose a total of, I had 6 volts to start with, I've used up 4 going on the backside, there must be 2 volts going through this parallel arrangement. So between this spot here and this spot here, they only lose 2 volts. But since it's parallel, an electron has to lose it whether they go to the left side or the right side. So now I'm going to go ahead and do each one individually. I'll do the left side first. V equals IR. I've got 6 volts is equal to I times, not 6, 2, sorry, 2, right? Because 2 is all I have left over. Times R, which is 3. And I get I equals 0.667 amps. And if I do the other one, I get V equals IR. I got 2 equals I times 6. I get I equals 0.333 amps. And I should check, because I know it's splitting right here. The current, where is my pen? That pen's way over there. Okay, my current coming out of the battery is splitting, right? So it's going this way, so it's going this way. All that can't go one way or the other. Some has to go one way, so it has to go the other way. Because of that, those two have to add up to that which is coming out of the battery. No 1 amp's coming out of the battery, so I check 0.667 plus 0.33. It confirms all my amperage. All my amperage is there, because those two add up to 1, all right? And so I think I'm done. So that's my currents going through each one of these particular things. All right, and so that's the way you do problems 2 and problems 3.